Hello everyone, I am Yangguang Shi from Technion. Today I will talk about our research work on online pigeon with the vanishing regrets. This is a joint work with Professor Yuval Emek and Professor Shay Kutten. In an online pigeon problem, we are given a main memory of size n and a cache of size k. The request over the pages in the main memory comes in an online fashion in T runs. At each run T, if the requested page segment T is not in the cache configuration, then we see that a cache miss happens. In such a case, the algorithm needs to invoke some page in the cache configuration and bring the requested page in. The cost of an online paging algorithm is defined to be the number of the cache misses, and the objective is to minimize the number of the cache misses. Given the full sequence of the paging requests, we can define the next arrival time net of a page I with respect to a run T to be the first round of T when the page I is requested. In Bleeded work in 1966, it is proved that the optimum can be achieved by an offline algorithm which always invokes a page with the largest nuts. We refer to such an algorithm as furthest in the future fit F. The regret of an online paging algorithm is defined to be the difference between the cost incurred by this algorithm and the minimum. Our goal is to design an online paging algorithm with a vanishing regret, which means that the ratio of the regret to the number of the runs capital T tends to be 0 when T tends to be infinity. However, an online paging algorithm with a vanishing regret is impossible under the conventional setting. Consider the scenario where the n equals to k plus 1 and the request sequence is generated uniformly and independently at random. It can be proved that in such a case, the expectation of the optimum is upbounded by big O T over K log K, while the expected cost of any random algorithm arc is lower bounded by omega T over K. Therefore, in our work, we will consider a setting where the online paging algorithm can receive predictions which can be possibly generated by machine learning algorithms. In particular, in a NAT predictor, the predictions are generated as a sequence as the predictions of the real nuts, and these predictions are generated in an online fashion. And for a NAT predictor, we define the cumulative prediction error to be the number of the runs when the predictions do not match the real nuts. Different from the related works focused on the single predictor case, in our work we consider the multiple predictor case. These multiple predictors can be implemented with the machine learning forecasting algorithms that are trained over different datasets or using different machine learning models, like the models that are robust to adversarial attacks. We make an assumption that when we are provided with accesses to multiple predictors, then at least one of them has a low cumulative prediction error that is sublinear in T. We refer to such an assumption as a good predictor assumption. Since the predictions of a NAT predictor is generated in an online fashion, there are two models to define how we can access the predictions. The first one is called the full information access model. Under such a model, the prediction of every predictor is revealed to the main algorithm at every round. The second one is called the bounded access model. In such a model, the main algorithm needs to make a choice over the predictors, and then it can only access the prediction of the chosen predictor at the current run. So obviously, the second model is more interesting, but also more challenging from the perspective of techniques. Now our main results are summarized as follows. We will start with the single predictor case. And for the single predictor case, we develop an algorithm SIM which simulates the operations of theta f, but replacing the real nuts with values that are derived from the predictions. And we prove that such an algorithm has a regret of big O or eta, which is the cumulative prediction error, plus k, which is the cache size. By the good predictor assumption, such a regret is a vanishing regret. For the multiple predictor setting with the full information access model, we can run our algorithm SIM with respect to each given predictor and in parallel, and then mix them with the random algorithm proposed by Blum and Birch in 2000. In this way, we can get a vanishing regret for the multiple predictor setting like this, and the full information access model. However, the algorithm proposed by Blum and Birch in 2000 requires to know the cache configuration of an algorithm that always follows a fixed predictor, which is unavailable in the banded access model. So to overcome this obstacle, we will utilize some combinatorial properties of our algorithm SIM proposed for the single predictor case to show that such an algorithm can always be chased without knowing its current configuration, cache configuration. And in this way, we obtain a vanishing regret for this banded access model. And it is expressed as this formula. Now I want to talk about something about the measurements of the prediction errors. In the related works, the cumulative prediction errors is often measured with the L1 norm, which is defined to be the L1 norm of the prediction sequence minus the sequence of the real nuts. Recall that in our work, the cumulative prediction error is defined to be the number of the runs when the prediction doesn't match the real nuts. And we also call this measurement as the number of the error runs. And it is easy to see that the number of the error runs, it is never larger than the L1 norm. Meanwhile, the L1 norm, it can be omega t times larger than sharp error runs. So we can see that the measurement that we have already described is better than the measurement used in these related works. In some related works, in their analysis, not their main result, they also consider another measurement, the number of the inverted pairs. For a pair of runs T and T prime, we see that they are an inverted pair if their real nuts and their predictions form across like this formula. And we define the number of the inverted runs to be the number of the runs T such that there exists another run T prime so that T and T prime form an inverted pair. And we can prove that the number of the inverted runs is at most 2 times larger than the number of the inverted pairs. However, the number of the inverted pairs, it can be omega t times larger than the number of the inverted runs. So we can say that the number of the inverted runs is actually better than the number of the inverted pairs as measurements. And the number of the inverted runs and the error runs, these two measurements are incomparable because we can construct instances so that the former one is omega t times larger than the latter one, and vice versa in another instance. And now we define a refined measurement of the prediction errors. It will count the runs that are counted by both the error runs, sharp error runs, and the inverted runs. So as you can see, it's such a measurement, it will be stronger than all these measurements discussed above. And although our main results were described with these measurement error runs, they also hold for such a stronger measurement. Now let's talk about the related work. First, in the paper by Lycoris on et al. On ICML 18, and in the paper by Rohaji on standard 2000, they consider the online paging problem with the single predictor, and their results are expressed as competitive ratios. Their competitive ratios cannot be converted to a result in the form of a vanishing regret. This is because their algorithms are based on the marking algorithm, and we prove that any marking algorithm cannot give a vanishing regret even when they are provided with the fully correct prediction sequence. In the paper by Wei on approach random 2020, he also considered the online paging problem with the single predictor. Our result for the single predictor case can be viewed as a refinement of his result because we are using a stronger measurement of the prediction errors. In the paper by Antonio Diaz et al. On HTML 20, they consider the single predictor setting for the online problem of the metrical task system, which is a more general system than paging. However, the measurements that they use for the cumulative prediction errors is incomparable with the L1 norm, and it is also incomparable with our measurements. In the paper by Golapudi on ICML 19, they consider the online scale rental problem and the multiple predictor setting. Notice that in the online scale rental problem, the length of the requests is implicitly bounded by the cost of purchase or buying the sky equipments. However, in our case, the challenge mainly comes from the unbounded request sequence. This is a major difference between our work and their work. So now let me describe our algorithms and our analysis. We start with the single predictor case and propose an algorithm sim which simulates the optimal algorithm fit F, but replacing the actual nuts with the remedy predictions defined as the follows. So if we do not look at this colored line, then the remedy predictions, it works as follows. It will initialize the remedy prediction of every page to be capital Z plus 1 for some large enough capital Z. And then it will update the remedy predictions to the given predictions of a page whenever this page is requested. So this is a very easy explanation, clear explanation, but we need to know what this colored line want to say. I want to explain what this colored line want to say. And let's first see this blue part of this colored line. And this line is necessary for us to get rid of the L1 norm measurements and accommodate the error run measurements. This this blue part, it can be interpreted as correcting the predictions that has already been found to be wrong. And I mean, the pages that are predicted to arrive earlier or not, but hadn't arrived. So let's see an example. Suppose that the n equal to 3 and k equals to 2. The initial cache configuration contains page 1 and 2. In reality, the page 1 is only requested at the beginning and the end. But in prediction, the page 1 is also requested at the round 3. And without the blue part, then we can see that after round 3, then the page 1 always has the smallest next arrival time, and it is never evicted from the cache configuration. In such case, it will cause a loss of omega t. Meanwhile, the error round, it will give a cumulative error of a constant. So to accommodate these measurements, we do need these blue parts. Now let's see these orange parts. This is an additional condition to help us to work with the measurement inverted rounds. And so still consider an example where we still have n equal to 3 and k equal to 2. And in the request sequence in reality, the page 1 is never requested. However, in the prediction, it is requested at the beginning. And in such a case, without the orange parts, then at round 2, our algorithm will update the prediction of the page 2 to capital Z and may evict it because it has a very large remedy prediction. And then at the round 3, it may update the remedy prediction of page 3 to capital Z and may evict it, and so on and so forth. And in such case, our algorithm may have a loss of capital T. However, the measurement sharp inverted rounds, it will give a cumulative error of a constant. So in such case, we need the first part of this original first inequality of this orange part to help us to deal with these measurements. And the second measurement is to ensure that the inverted pairs that we count are not caused by our operation of increasing the remedy prediction of some page to a large enough Z. Yes, this is the basic idea of setting the remedy predictions. Now let's see some definitions and notions that we will use in our analysis. For the cache configurations of the algorithm fit F and sim, we define the intersection to be the set of the pages at round T that are both in the cache configurations of them. And the distance is defined to be k minus the size of the intersection. We define the troublemakers to be a set of special rounds that satisfies this condition. This condition can be interpreted as follows. At a troublemaker round T, our algorithm sim will evict a page from the intersection. But the optimal algorithm fit F will not evict this page. Instead, it will keep this page in its cache until it is requested for the first time after T. And we call this time as round T prime. So as we can see, our loss will be increased by 1 at the round T prime because a cache miss will happen to our algorithm but not to the algorithm fit F. That's why we call the round T as the troublemaker. And so we have such a theorem. The loss of our algorithm sim is bounded by big O, the number of the prediction errors, plus K, the cache size, plus the number of the troublemakers, minus the number of the rounds where the loss decreases. The basic idea of proving this theorem is as follows. First, a round that increases the distance will neither increase nor decrease our loss. This is because in such a round, both the optimal algorithm fit F and our algorithm sim need to invoke some page, and in fact they need to invoke different page in the intersection. So the loss doesn't change in such a round. Second, the number of the rounds where the distance decreases, it can be upbounded by the number of the rounds where the distance increases plus the cache size. This statement is obvious. And three, a round that increases the distance can always blame a round that is counted by the cumulative prediction error, because otherwise the algorithm fit F and the algorithm sim shouldn't invoke different page in the intersection. And fourth, a round that is counted by the cumulative prediction error can be blamed by at most twice, because each time it is blamed, the round that is the page that is requested at that round will be evicted from either the cache of the fit F or the cache of sim. So putting all these statements together, we know that we can reduce the problem of analyzing the cost to counting the rounds where the distance doesn't change, but our loss increases. And it can be further proved that such kinds of runs are caused by either a run that increases the distance or a troublemaker run. So now it remains to count the troublemaker run. And in our paper, we propose a labeling mechanism to count the troublemakers. And our main idea is to show that every troublemaker can be mapped to either a round that is counted by the cumulative prediction error or a round that the loss decreases. And we will use the labels to ensure that not too many pages are mapped to the same round that is counted by the cumulative prediction error or the round with the loss decreasing. And in fact, we will show that the first mapping will be a 2-to-1 mapping, and the latter one will be a 1-to-1 mapping. And for a troublemaker round gamma, when our algorithm sim invokes a page like this bare page, and then we will find a page in the cache configuration of our algorithm, but not in the cache configuration of the fit F. And such an algorithm, such a page should be unlabeled, like this cat page, and we will label it until in the invoked page, the bare page is requested. And now we will consider three cases. The first case is that the labeled page, the cat page, is requested earlier than the invoked page, the bare page. And our algorithm sim keeps the cat page in its cache configuration until it is requested. Then, as you can see, at this cat round, there will be a cache miss happen to the fit F algorithm, but not to our algorithm. So at this cat round, our loss will decrease by 1. So in such case, we can map this troublemaker to a loss decreasing round. The second case that we consider is the bare page is requested earlier than the cat page. And in such a case, we can see that the round gamma can be mapped to a prediction error, because without a prediction error, the algorithm sim should invoke the page cat page instead of the bare page, because the cat page arrives later than the bare page. The third scenario is more complicated. Here we still assume that the cat page arrives earlier than the bare page. The cat page is the page labeled at the beginning. And however, our algorithm may evict this page before it is requested for the first time. And in such case, we will find another unlabeled page in our cache but not in the intersection, like this rabbit page. Then we will label this rabbit page. This is like a recursive case of the two cases that we discussed above. And we will keep finding the unlabeled pages in our cache and but not in the cache of the FitF. And we will label it so on and so forth. The question is how to ensure that we can always find an unlabeled page to label in our cache but not in the intersection. One important observation here for this question is that the bare page, it will exist in the cache of the FitF, but not in the intersection during this whole period. So by symmetrics, we can always find a page, may be different pages in different rounds, but you can always find a page throughout this period that is in our cache, but not in the cache of the FitF. So yes, this is the basic idea to find the unlabeled page. In this way, we solved our problems for the single predictor case. And now let's check the multiple predictor citing. For the full information access model, as mentioned earlier, we will simulate our algorithm sim with respect to each given predictor. And we will mix these algorithms with a random algorithm proposed by Blum and Birch in 2000. In their algorithm, they will run a stateless online learning algorithm over the predictors. And each time the online learning algorithm chooses a new predictor, their algorithm will make a switch between the cache configurations to catch the new algorithm with respect to the new predictor. And their algorithm can help us to get a vanishing regret for the full information access model. However, their algorithm needs to know the cache configuration of every algorithm follows each predictor. This information is unavailable under the banded access model. So to overcome this obstacle, we will use a chasing procedure instead of switching the cache configurations. In particular, we will restart sim. Every time the online learning algorithm chooses a new predictor, we will restart our algorithm sim in an unset manner from the current cache configuration with respect to the new predictor. And this technique works very well because our analysis on sim for the single predictor case, it holds regardless of our initial cache configuration. And particularly, even if our cache configuration is different from the initial cache configuration of the FitF algorithm, our previous analysis still holds. This property help us to ensure that the chasing procedure works well. And another question here is that how could we build the feedback to the stateless online learning algorithm? Because in the banded access model, under the banded access model, we cannot know the cost incurred by the algorithm that always follows the same predictor. So this problem is non-trivial. And can we directly use our cost, or cost caused by our algorithm as an approximation or estimation of the cost of the algorithm that always follows the fixed predictor? The answer is no, because the cost caused by our algorithm is a stateful cost, and we cannot directly fit it to a stateless online learning algorithm. We solve this algorithm by omitting the first key different requests after the algorithm sim is restarted, and we only fit the costs incurred by the remaining page requests to the stateless online learning algorithm. And we prove that the cost that we fit to the online learning algorithm is actually stateless. This solves our technical problems and help us to get a vanishing regret for the multiple predictor setting. That's all. Thank you.